Now, what about compounds that are not ions? In this case, we have two polar compounds. This is alcohol. This right here is the discrete molecule alcohol. And you know that alcohol is very, whoops, it goes around, is very soluble in water. That's the alcohol right there. It's ethanol. Very soluble in water. Like we saw the example at the very beginning of this unit of 70% isopropyl alcohol. You can't tell the difference between the alcohol and the water because they're completely miscible. They form homogeneous solution. Here's an example of alcohol and water. You know that's the case too because alcohol that people drink, for example, beer or wine or vodka, whatever, it's not 100% alcohol. It's normally some percentage of alcohol and the rest of the percentage is water and flavoring. And so you can see why they mix so well though, because the alcohol has the OH group, and then the waters, of course, have the OH group. So there's this part of the molecule is capable of undergoing hydrogen bonding with the waters. Okay, and I want you to point out here that remember, hydrogen bonding can occur when the compound, this is the water, contains an oxygen bound to a hydrogen or a nitrogen bound to a hydrogen or a fluorine bound to a hydrogen. If the compound contains somewhere in it a bond with oxygen to hydrogen, nitrogen to hydrogen, or fluorine to hydrogen, that compound is going to be able to have a stronger than normal dipole attraction to another molecule that also has the OH, NH, or FH. And in this case, the OH and the ethanol, there's also hydrocarbon part of it, but the OH attraction is so strong, this is going to be very soluble in water. Notice also that even though there's all these other hydrogens, 5 other hydrogens on this molecule, you do not see hydrogen bonding occurring between this oxygen and that hydrogen. That's because this hydrogen is not itself bound to an oxygen, a nitrogen, or fluorine. Okay, so just because you have hydrogens in the molecule doesn't mean the molecule is going to undergo hydrogen bonding. The hydrogens within the molecule have to be bound to one of these very electronegative elements. Okay, so the hydrogen bonding is only occurring around the OH group in the ethanol. Nevertheless, it's completely miscible in solution. Okay, which leads us to sugar water. The sugar water, this is a molecular model of structural model, or structural formula for sucrose. That's table sugar, and you can see in the table sugar, it's a large molecule. It's a hydrocarbon because there's carbons and hydrogens bound to it, but it also has a lot of OH groups. Okay. And remember, the OH groups then will be capable of undergoing hydrogen bonding with another molecule that has OH groups in it, which would be water. And so what happens with the sugar when it dissolves, the water molecules, so you've got a cube of sugar dropped in water, the water molecules are going to approach the hydroxide groups, which also would be sometimes called hydroxide group or called alcohol functional group, and it's going to create these very strong intermolecular forces, the hydrogen bonding. So this is the hydrogen bonding occurring all over the place, and so enough water can get around all these OHs to pull the water molecule, or the sugar molecule into solution as well. So this is an example of a two polar species, both of which are capable of undergoing very strong hydrogen bonding intermolecular forces, and that's why sugar is so soluble in water, because of all of these OH groups on the sugar.